In this lesson, we're going to be talking about techniques for computing limits. And the first thing you want to do is kind of recognize what kind of an equation do you have. So a lot of them are either polynomials or rationals. And so a polynomial is like linear, quadratic, cubic, graphs that don't break, right? They're just kind of smooth curves. And remember what an idea of a limit is that a limit is always about what you're approaching from either side. So if your graph is smooth and there's no breaks, then you're approaching the same value always from either side of whatever value you're plugging in. So the short of this is that if it's a polynomial and you want to find the limit at a particular point, you just plug it in. And that's it, because there's no breaks. It's not a piecewise where you're heading at different values. There's no asymptote to kind of break up the graph. And so polynomials are really nicely straightforward. A rational function is okay unless that they have potential domain issues. And so you have some variables on the top, variables on the bottom. There's possible domain issue with your denominator being 0. So as long as your limit is not the problem number, the domain issue, then it's as straightforward as polynomial because everywhere else is connected, right? It's approaching the same thing from either side on every other ration. So all you have to do is this the problem number? If it is, then there's some additional stuff we have to do. It's not the problem number, plug it in, simplify your fraction, and that's your limit, right? So that's really all this means is anytime you're doing a limit, the very first thing you're going to do is plug it in, see what happens, right? And so let's start off with this. We have ourselves a linear. So I know that a linear is connected everywhere, right? There's no breaks or anything like that. So that's telling me that if I'm going to find the limit, as x approaches 3, that just means that I am going to plug in 3. Oops, sorry, skipping a step. The limit as x approaches 3 of f of x is us plugging in the number. All right, so we are multiplying 1 times 3 halves. Sorry, 3 times 1 half, which is 3 halves, minus 7. And I'm going to make this denominator match. So it's going to be 3 halves minus 14 halves. And if I put those two together, I'm getting a negative 11 halves or negative 5. All right, and I know that if I was graphing a linear, this has a y-intercept down here at a negative, going up 1/2. I'm going to be at a height negative 5.5. So there's my value. So I'm definitely approaching the same thing. And I knew I was because of the fact that we had a linear. All right, so if I'm looking at this, what kind of situation do we have going on here? So this, g of x equals 6, is a constant. Right? It's just a constant y equals 6. So visually, you have basically just a horizontal line. We are looking at the limit as x approaches 2. That's supposed to be approaching 3. Point in there. Here we go. So there's our 2. There's our value. We're approaching the same thing from either side. So the limit as x approaches 2 of g of x, there's no equation to plug in. It's just 6. All right. So you're going to get all sorts of different situations. And so let's make sure we're comfortable with some of the things that if you have some sort of a function that has multiple pieces, you can bring them up individually and focus on each piece individual and then add those values together. Same thing with subtraction. If you have a constant, it's usually like 2 times x squared. You can take that 2 out and then just do the limit of the x squared and then multiply it by 2. If you have a multiplication going on, you can treat them independent and then multiply them together. Division, same thing. You can do the limit of the numerator, limit of the denominator, and simplify it out. Again, making sure that your denominator is not 0. And then if you have something with an exponent on it, this one's really nice that you can rewrite the whole thing and then raise it to the power. And so you can get your value and then cube it or whatever it is. If you have a fractional, this basically means you have a root going on. So square roots, cube roots, fourth roots. However, this works. You can kind of treat it the same as we do for this one by pulling the exponent off it as long as it is even. So you're looking at like a 1/2 power, a 1/4 power, 6th power. And so that's a square root, a fourth root, a sixth root, those types of things. All right, so let's do a couple real quick. that this doesn't really have equations, but they're giving you values for it. So let's make sure we're comfortable kind of rewriting some stuff using these properties. So if you have something that looks like this, you could rewrite the whole thing as the limit as x approaches 2 of f of x minus the limit as x approaches to g of x, all divided by the limit as x approaches to of h of x. And since they give us this value, they give us this value, and they give us this value, you can just sub those all in. So you're looking at a 4 minus 5 divided by 8, which gets us a negative 1/8. Right? Then same kind of thing here. Let's see if we can make this a little bit easier for ourselves. So we could rewrite this as 6 kind of times the limit as x approaches 2 of f of x times the limit as x approaches 2 g of x plus limit x approaches 2 h of x. And that whole thing multiplied by 6. So let's go through all of these pieces. So that's going to be the limit of f of x. It's going to be 4. So 4 times 5 plus 8. Let me put the bracket here, there, because the 6 is only applying to the f times the g. So then that 6 is going to be multiplied to only those two. And then we'll add 8 to it. All right, so we're looking at 20 times 6 is 120 plus the 8 gives us 128. All right, and then the last one is for this cube. We can do the limit as x approaches 2 of this g of x. And then we can get that answer and raise it to the third power. It's kind of the math that we're looking at. So that value is g of x is equal 5 cubed is 125. Okay, so that's a little bit of an introduction. Then we'll start to do actual problems and kind of see what happens with those types of things.